We can get started, ma'am. Meanwhile, the others they can join.
Thank you. Uh, Hi everyone. So welcome to the week 2 of the internship program, and today my team Sharmila and Akansha will be taking this session. I understand that you had some queries for the assignment that we had given. We wanted you to do some understanding and some kind of brain racking things, but it's not at all difficult. By the end of the presentation, once we take your questions, I'll give you a few more examples for the assignment for the previous week. Okay, with that, I hand it over to Sharmila. Stage is
Yeah,
yours.
thank you.
Over to you.
Thank you, Richa.
Okay, can share
Yeah.
your screen.
Yeah, hi team.
Uh,
Richa, can you able to see the screen?
yes, now I am.
Yeah,
Thank you.
yeah. I'll start. Hi team, good evening.
Sharmila, just
Yeah,
go to the previous slide. I just want to take one snapshot. The title slide.
yeah,
Yes, just hold on. Please proceed.
yeah. Good evening, team. Am I audible, Richa?
Good evening, ma'am.
Yeah.
Yes. Please proceed.
So, yeah, in our first session, we set the foundation by understanding the broader concepts of HEOR, RWA, HTA, and pharmacoeconomics, right? So we also explored the skills, scope, and career opportunities in this field, giving us a big picture view of how these disciplines shape healthcare decision making and market access. Okay. Now, in today's session, we will take a step further and move from theory into application. Okay, guys, we will look at the study designs and tools that generate the kind of evidence we discussed earlier. Specifically, here we will cover observational study designs, which is the backbone of generating real world evidence, pragmatic clinical trials, and comparative CER means comparative effectiveness research, that is bridging the gap between traditional clinical trials and real world practice. And third one is decision analytical modeling basics, which allows us to synthesize data and support healthcare decision making when direct evidence is limited. This way, we are building from the what and why of HEOR and RWE into the how, the actual research designs and methods that bring evidence into practice. So among study designs, observational studies are especially important because they allow us to study what happens in real life outside the means real life in the sense outside the carefully controlled conditions of the clinical trial, and that's our focus now. Okay, so to understand why observational studies are important, we first need to appreciate the journey of clinical research itself. Okay, so now we'll see. In 562 BC, King Nebuchadnezzar observed how diet influenced health. He gave some soldiers vegetables, others meat and wine. That was crude, but it showed curiosity about comparing groups. Okay, And in 1537, Parry, what he has done, he is actually a surgeon, French battlefield surgeon, changed medicine forever. He was treating soldiers' wounds with boiling oil. Okay, the standard practice. But when he ran out, he used a gentler ointment of egg yolk, oil of roses, and turpentine. To his surprise, the soldiers treated with the ointment recovered better. So this was the accidental comparative trial. Then in 1747, James Lind conducted uh, what is often called as it is a first clinical trial on a sheep plagued by scurvy. He divided 12 sailors into groups. One group got vinegar, another cedar, another seawater, and one group citrus fruits. So the sailors who ate oranges and lemons recovered rapidly. So Lind's study was a simple but groundbreaking. So it showed diet could prevent disease like so disease. So like this one in 1800 and 1943 like that. And next, if you do fast forward to the 20th century in 1947, the streptomycin trial for tuberculosis was the first randomized controlled trial. Patients were randomly assigned to receive streptomycin or not. So it is removing allocation bias. Soon after, the first double-blind trial was done for patulin in the common cold, ensuring neither doctors nor patients knew who was treated. So this progression shows something important as science advanced, we became more rigorous in testing treatments. But this is the key, RCTs, while powerful, are not always enough. They are done in ideal conditions. Observational studies, in contrast, show us what happens in the messy, imperfect real world. Okay, then um, so let's classify study designs. Okay, here the critical question is in this slide, whatever we are seeing now, did the investigator assign the exposure? If yes, then it's experimental study. The researcher controls who get what, like in an RCT. If no, then it's an observational study. Here researchers watch what happens naturally. Within that, we can divide studies into, means within the observational study, we'll divide into descriptive and analytical. What is descriptive? It is simply describing what's happening. Means, for example, reporting the 10% of the population has diabetes. And if it comes to analytical, asking why or how. Example, does smoking increase lung cancer risk? So think of descriptive studies as reporting the news. Okay. And while analytical studies are investigative journalism, they dig deeper to understand causes. So in this, here we are seeing the first way of classifying study designs by the role of the investigation. So here the critical question is, did the investigator assign the exposure? If the researcher actively assigns who receives the treatment or intervention, the study is experimental. For example, assigning one group to drug A and to another to placebo, like cause and effect relationships and all. If the researcher only observe what is happening naturally without interfering, the study is observational. Okay, the single question forms the backbone of classification. It determines whether a study is about controlling the exposure or simply watching real world event unfold. So Why is this distinction important? Because the level of control versus realism affects both the validity of results and how we apply them in practice. Okay. And another way of classifying studies is by investigative purpose. So here, descriptive study means it is the observational study, right? Descriptive study and analytical study. So we have already seen that they describe descriptive study, describe the patterns. For example, what is the prevalence of diabetes in India today? They don't test associations, they report what is. Okay, analytical studies, these go deeper. They ask, is there a relationship between obesity and hypertension? Does smoking increase the lung cancer risk? Means they are seeing the association. So, descriptive studies are like photography, a snapshot. Analytical studies are like detective work, looking for causes and associations. But both are important. Descriptive study help identify problems. Analytical study test hypothesis and provide the evidence base of intervention. Okay. In and another the types of experimental study design, since experimental study design, the investigator assign exposure as already we have seen. This is the world of clinical trials. So the key features are participants are allocated into different groups. Each group receive different interventions. At the end point, outcomes are compared. So when randomization is used, bias is minimized. That's why we are doing the randomization studies. That's so, and also they are also called as gold standard. But remember one thing: experimental designs are not always possible or ethical. We cannot random people to smoke or not smoke. That's why observational designs remain critical. Okay. Then come to type of randomized controlled designs. So RCTs themselves comes under different flavors depending on how interventions are given. Let's walk through them. Okay. Parallel design. These are the simplest and most common. Most of you people know about the parallel design, right? And participants are randomized into separate groups, each receiving one intervention. And for example, one group gets a new diabetes drug, another gets placebo. Okay. And if you see the parallel design, so most of you know, just I am just showing the papers. Here it is something like that. So it is randomized parallelly, two groups they are parallelly assigned, right? So 78 in one group and 81 in another group. This is the parallel design. Okay. Then comes to crossover design. Here participants receive receive both treatments one after the other with a washout period in between. I'll show the references once all the things over. Okay. And here the example is patients first get drug A, then switch to placebo. This reduces variability because each person serve as their own control. Anyways, I'll show.
Put in full screen mode.
Yeah. Oh.
Make it full screen, Sharmila.
Yeah. Yeah.
Yeah.
Okay. Here, and the third classification is factorial design. I'll show all the references at the end. Okay. And in the factorial design, participants are randomized to receive combination of two or more interventions. So, for example, testing drug A and drug B at different doses in all possible combinations. So, this design helps test interactions between treatments. And fourth one is cluster randomization. So instead of randomizing individuals, we randomize groups like schools, villages, or clinics. So groups, they are randomized. For example, one set of schools adapt a new teaching method, another continues standard practice like that. They group and randomize. So in this four, each design has strengths and is chosen based on the research question. Okay, now another way to understand experimental studies is through the phases of clinical trials. So that is all of you know phase 1, phase 2, phase 3, and phase 4. Phase 1 is first in human, small groups, often healthy volunteers. What is the goal here? We are testing safety dosage. Around 70% of from phase 1 moves to next phase. And in the phase 2, larger group of patients with a disease. So here what is the goal? Uh, Preliminary effectiveness, continued safety from phase 1. So from here, about 33% of the patients, they'll go to phase 3. So in phase 3, large multiple center trials will happen. So hundred or thousands of patients involved in phase 3 studies. So what is the goal here? Here they are confirm the effectiveness, monitor side effects, compare to standard care. From the phase 3, only about 25 to 30% succeed. Okay, the drugs will move to the next phase from here. So, in phase 4, post marketing studies will happen. So, what are there? They'll monitor safety and effectiveness in the general population, roughly like 14% of the drugs entering at, if you see whole, 14% of the drugs entering trials reach approval. So notice how attrition happens from phase 1 to phase 4. Only a fraction of candidate drugs survive this funnel. That's why trial design and evidence strength matters so much. Okay, next, now let's shift to, till now we have seen the uh, experimental designs, that is randomized studies. Now, so we'll see the observational analytical designs. So here, this is case control studies. So here, what is happening? Start with disease status. Okay, like case versus control, and look backward the exposure. For example, patients with lung cancer versus those without, and comparing smoking history. Okay, what there are pros and cons in this design. The pros are quick. This case control studies are quick, inexpensive, suitable for rare diseases. So if it comes to cons, they'll recall and selection bias will be there. If you see the cross-sectional designs, here it is a snapshot in time. So measure exposure and outcome together. For example, survey of obesity and hypertension prevalence in a community. So here the pro is easy, good for prevalence. Cons are cannot establish causation. Okay, And if it comes to cohort studies, they'll follow exposed versus unexposed groups over time. For example, smokers versus non-smokers followed to see who develops lung cancer. So, what is the pros? Stronger evidence, incidence rates, and relative risk. We can find from this. But what are the cons? Time consuming and expensive. So, together, these all gives us a toolkit to study exposures and outcomes when experiments are not feasible. Okay, next. When it comes to cohort studies, they again divided into two groups, prospective or retrospective. So prospective cohort is forward looking, like we start with a group at baseline, record exposures and follow them into the future. For example, following smokers versus non-smokers for 20 years. That is the
Hi,
prospective cohort.
sorry Sharmila to interrupt. Can you please change the mode of the slide from presenter to viewers? Students are requesting to remote. If we can click down,
Ma'am, near
down.
the maximizing button, there's a slide, so I think you can try that.
Yes.
Maybe that help.
Below your slide, there is a zoom in or out button. Just next to that. Yes. No,
Is
okay.
it fine?
No, it's still the same.
What happened? Is it not able to, not you are not able to see? Akanksha, what happened?
Maybe they so we can see two screens, one the bigger one, the other next slide is also visible. Maybe students want it the present slide to be on full screen.
Okay. Can you share the screen, Akanksha, if I share to you?
Let
Or
me
is there any, you can just check now? No? Is it in the same way?
it's in the same way. Let me try sharing. Okay, let me try sharing.
Actually, some slide. I'll share this. Wait, I'll stop sharing and I'll share this PPT with you. Okay.
I have the version you shared, right?
No, no.
Okay.
Wait.
Where are you sharing, Sharmila?
In WhatsApp, is it fine?
Okay,
Can I
okay.
send through mail?
Yes, please. No problem.
Yeah, wait.
Sorry, guys. Any problem in sharing the screen? Shall I share?
No,
Yes,
no problem.
No,
Akanksha
it's
is
okay.
going to.
No, I'll share. I'll take the control.
Okay.
No worries at all. Just
I'm Aditya. I'm sending the screen. This one. Please share this. Okay.
no problem at all.
2 more slides added. Fine. That's it.
I have received a Word document, Sharmila. You want me to share
not
that?
that one. No,
Oh,
not that one. Okay.
okay,
not
okay. I'm just sharing my screen, okay?
Yes.
Can you see the presentation?
Yes. Yes.
Which slide number, Sharmila?
Slide 12.
Slide
12.
12.
Yeah.
Okay. This one?
Yeah.
Okay. I'll make it full screen.
Yeah.
Go ahead.
Yes. When it we have seen the cross-sectional studies, right? Cohort study, case control study. Now we are seeing the types of cohort studies. So these are prospective and retrospective. So here, prospective cohorts are they are forward-looking. We start with a group of baseline, record exposures, and follow them into the future. So, for example, here if you tell following smokers versus non-smokers for 20 years, and if it comes to retrospective cohort, backward looking, we start today but use historical records to reconstruct exposures and outcome. For example, using hospital archives to see whether past alcohol use was linked to later liver disease. So, both designs have strengths. Prospective studies cohorts give cleaner data. Retrospective cohorts are faster and cheaper, but rely on existing data quality. Go to next slide, Rich. So here in this, let's compare experimental and observational studies directly. So I'll tell in one word. So experimental is high control, randomization possible, bias minimized, strong internal validity, but often artificial and less validity. Okay, when it comes to observational, real world validity and can study exposures not ethically assignable but more prone to bias, observational. This is the classic trade-off, control versus realism. That's why we need both. Evidence-based medicine builds on integrating both streams of evidence. Next slide, Rich. So, if you are weighing pros and cons for the observational studies, types of observational studies, that is cross-sectional, case control, and cohort studies, here, now let's look more deeply at the advantages and disadvantages of this different observational study designs. So, here in this slide, we are summarizing the strengths and limitations of cross-sectional case control and cohort studies. So what is the cross-sectional study? What are the advantages of cross-sectional studies? Okay, these studies are quick and inexpensive. You can conduct a survey in a community and get answers in weeks, not years. Okay, it is very quick. So they require fewer resources. Okay, no longer long-term follow-up, no repeated patient visits. So they are excellent for measuring prevalence. For example, what percentage of cities population has hypertension today? Okay, what are the disadvantages? So the if you tell the biggest challenge is casualty because exposure and outcome are measured at the same time, you cannot determine which came first. So And multiple explanations may exist for the absurd association, and they are not efficient for rare diseases. If a condition affects only 1 in 10,000 people, a one-time survey will likely miss it. So think of cross-sectional studies as photographs, great for snapshots, but not for timelines. Then, if it comes to case control studies, the advantages are perfect for examining rare diseases or diseases with a long latency, uh, like one disease from asbestos exposure. Okay, they are, and also they are relatively quick and inexpensive compared to long-term studies. And also they require very less participants. You don't need to follow 10,000 people for decades. Instead, you can compare 200 patients with lung cancer to 200 controls. So, uh, there will be existing records such as hospital databases can often be used. So, and also multiple exposures can be explored for one disease. For example, lung cancer cases can be analyzed for smoking, occupational hazards, and air pollutions simultaneously. And if it comes to disadvantages, recall bias is common. Patients may misremember uh, exposures from years ago. And also, information may be difficult to validate, especially when relying on old records. And extraneous variables may not be fully controlled. Choosing the right control group is often tricky. If controls are not truly comparable, bias creeps in. Okay, like that, even case control studies also cannot provide absolute risk or incidence rates. So they can only estimate odds ratio. So while case control studies are excellent hypothesis generators, their results always needs cautious interpretation. Okay, if it comes to cohort studies, the advantages are cohorts allow us to track the sequence of events. Okay, starting with exposure, then observing outcomes. This makes it possible to study causality, and they allow examination of multiple outcomes from the same exposure. For example, smoking can be studied for its relationship to lung cancer, COPD, and also heart disease. So they're particularly useful for studying rare exposures like radiation exposure in nuclear plant workers like that. And they allow calculation of disease rates incidence, relative risk, and attributable risk like that. So if it comes to disadvantages, they require large sample sizes, especially for rare outcomes. They are susceptible to selection bias if follow-up is uneven or participants are lost. So cohort studies are like long moves, long movies. They take time and resources, but tell the full story of exposure to outcome. Next slide, please, Richa. Next, now let's compare experimental designs, randomized control trials. We have seen the observational studies. Now we'll see the experimental design advantages and disadvantages. So advantages of randomized control trials, or you all know as it is use uniform diagnostic criteria, often blinding, meaning neither patients nor doctors know who is receiving the treatment. This reduces information bias. So randomization balances out both known and unknown confounders, eliminating bias from baseline differences. They are statistically powerful and efficient, even for detecting small or moderate differences. And also, they are considered the gold standard because they minimize bias better than any other design. Okay, and if it comes to disadvantage, limited external validity. Already we have seen for whatever we have for the observational studies, it won't be there here. So there is limited external validity because patients are carefully selected. The results may not apply to the general population. Okay, for example, if you see elderly or multimorbid patients are often excluded like that. So recruitment is highly screened, limiting variability. Okay, RCTs cannot ethically be used for harmful exposures, like for example, forcing participants to smoke like that, and they are expensive, requiring years of follow-up and large infrastructure. So RCTs are powerful, but sometimes disconnected from everyday practice. Okay, keep this in mind. Okay, and if it comes to non-randomized controlled trials, advantages are they still use a concurrent control group, meaning results can be compared across groups. Outcomes are measured with similar rigor in both groups. And if it comes to disadvantages, the biggest problem is selection bias. Without randomization, if there is no randomization, there will be a bias, and groups may differ systematically in ways that affect the outcome. So, non-randomized trials are useful when randomization isn't feasible, but the results must be interpreted with caution. Richa, next slide, please. So finally, let's place everything in the evidence hierarchy. So here at the base, we have expert opinion and case reports, useful but lowest in reliability. Okay, moving up, we found cross-sectional cross-sectional studies and case control studies. Okay, higher still are cohort studies, then RCTs. Okay, at the very top sit systematic reviews and meta-analysis, which synthesizes multiple studies to provide the most reliable conclusions. And if it comes to levels of evidence, level A, level B, and level C, level A, high quality evidence, often from multiple RCTs or meta-analysis, and level B, moderate quality evidence from cohort studies or single RCTs, and level C, lower quality evidence from case control studies, expert opinions. And this pyramid helps us understand why not all evidence is equal, but also why every study type has its place. But for decades, the pyramid of evidence has been the go-to graphic in classrooms and lectures. Understand this to illustrate the hierarchy of evidence. But here's the problem. It leaves out the most important part of the story. The pyramid assumes that randomized trials automatically sit at the top, right? If you see, it is looking like that. While observational studies remains at the bottom. That might look neat in the diagram, but in practice, it's outdated and misleading. What the pyramid ignores, what it is ignoring. Randomized trials do not automatically guarantee high certainty, and observational studies are not always low certainty. In fact, a small, poorly conducted RCT can be less reliable than a rigorous, well-powered observational study. So this is where grade comes in. Okay, instead of ranking study designs in a rigid hierarchy, grade assesses the certainty of the entire body of the evidence. So, taking into account study limitations, inconsistency, indirectness, imprecision, and publication bias. So the result is more transparent, flexible, and trustworthy framework, one that reflects how evidence really work. Okay. Now, I think you people can understand what is the importance of all type of trials. Even observational trials are also very important. So now we once again revise type of observational studies, because here observational studies is very important. That's why I'm again revising that in the above context. When it comes to case control studies, these are retrospective. We start with the disease and look backward. And so we take mm, if we are designing the study, I can, and if it, I have one question to the team. You have, till now, you people have listened all these things. And I have one question. If you are designing any study, any case control study, how would you choose controls? Means, for example, I'll tell, we take 200 patients with lung cancer. Here the question. We take 200 patients with lung cancer and 200 without controls. We check how many in each group smoked. If smoking is much more common in the lung cancer group, right? So here the advantages is fast, relatively cheap, good for rare diseases. But I want to know, if you are designing this study, how would you choose controls? Would you select neighbors? Listen the question. Would you select the neighbors, hospital patients without cancer, or random community members? What is the right control? Please text in the chat. So I'll continue again. After this, I'll continue. I want the answer for this. Please write in the chat. If you are designing any study, how would you choose controls? Would you select neighbors, hospital patient without cancer, or random community members? Good going, guys. Good going. Yeah, most of you people are in a right path and you have given a right answer. So now I'll answer the queries. If anybody or not understand, I'll answer the query. Please listen. Okay. What is the principle here? Controls must represent the same source population that produced the cases and be selected independently of exposure, right? The chance of being picked must not depend on smoking. First best choice is, most of you people, you are very right, random community members from the same catchment as the cases. So here the sample frame is practice list, voter roll, census list, random digit dialing, like that. So why we are choosing them as a control? Because their smoking distribution should mirror the population that gave rise to the lung cancer cases. So it is the strongest external validity. But another one, second acceptable alternative is also there. That is with hospital clinic controls, unrelated conditions. Okay, recruit in the same, if it is not possible, randomly. So we can go to the hospital and clinic controls, recruit in the same hospital and time window as cases, and exclude diagnosis linked to smoking. For example, COPD, MI, PAD, head and neck cancers, to avoid all this, avoid the bias and all. And Good when community sampling is infeasible and helps balance healthcare seeking behavior. Okay. And third one, usually avoid use consciously neighbor controls. But if you go to pros and cons are, pros are fast, similar, but cons are overmatching on neighborhood exposures and what we can then air pollution, outlet density, non-response bias, use only if nothing else is feasible, or as second control group for sensitive analysis. So in case control style, if you summarize that, the best controls are random community as, or very good, most of you answered that, from the same population that produced the cases, chosen independently of exposure. If that's hard, we can use hospital controls, but only with diagnosis unrelated to the exposure to avoid bias. Okay, and we can match age, sex, area, and time, give each control the case index days, and measure smoking the same way in both groups. Okay, so like that, we are adjusting the confounders and all. And neighbor controls are the last resort because of overmatching. So like that. Okay. So we have seen cross sectional. It is like a photograph or snapshot in time. And if it comes to cohort studies, these are longitudinal studies where we follow groups over time. And now let's step back. Why are these studies so crucial? Because all these observational studies. Okay. Because RCTs often exclude real patients, elderly people, pregnant women, people with multiple diseases, they are left out. But in the real world, these are exactly the patients doctors treat, right? So, observational studies include them. They tell us not just whether a treatment works in a controlled lab, but how it works in a real practice across diverse population in busy clinics and with all the complexities of real life. So this is why regulatory agencies, payers, policymakers rely on observational study for RWA, real world evidence. They complement RCTs, bridging the gap between ideal conditions and reality. Okay, guys. Next slide, Richa, please. So now that we have covered observational studies, let's bridge to the next level. Pragmatic clinical trials and comparative effectiveness research. Think of this as moving from traditional gold standard RCTs, which are rigorous but artificial, towards methods that combine rigor and real world relevance. Next slide. So let's compare. It is traditional RCTs. They have narrow inclusion criteria. Patients are usually young, healthier, and not representative of real population. And if it comes to controlled environment, specialized academic center and rigid protocols. And RCTs have surrogate outcomes like lab. Okay, this make RCTs excellent for internal validity, but weak for external validity. Okay, but when it comes to pragmatic clinical trials, they conducted in everyday clinics, hospitals, and also community settings. Okay, include diverse patient population, elderly, comorbid, socio-economical diverse, flexible protocols, and they are closer to real care delivery. Outcomes or that matter to patients like quality of life, hospital admissions, adherence. So, for example, testing a new diabetes drug in a RCT Like we'll see middle-aged, otherwise healthy patients, and outcome is HbA1c reduction. But in the pragmatic clinical trials, we'll see elderly patients, obese patients, those with cardiovascular disease, and outcomes are hospitalization, quality of life, and daily function. And now, I'll ask one question. If you are a policymaker, I have another question to the team. If you are a policymaker deciding whether to fund this new drug, which trial results would you find more convincing? The RCT with ideal patients or the PCT results in everyday clinics? Please text in the chat. If you were the policy deciding whether to fund this new drug, which trial results? Good, guys. You are on the path and you are very good. Okay. Okay, good, good. And now I'll answer the query. If all of you understand, okay. If any of you are not understanding, please listen to this. If I am a policymaker, I'll use RCTs to establish efficacy and safety. That is, can it work? So that's RCT. But I had base coverage and pricing for more on pragmatic trial evidence. Does it work? For whom and at what cost in routine care? Here's why external validity PCT include older, multimorbid and diverse patients treated in typical clinics. That is the people I will actually be funding. Okay. And relevant outcomes are they track hospitalization, adherence, quality of life, and resource use, right? So it drivers of budget impact and value also. And there will be a comparative relevance. But PCTs often compare against real standard of care regimen, not placebo. And if it comes to implementation signal, they reflect real prescribing behavior, monitoring, and persistence, critical for forecasting utilization and spend. Okay, what's the logic here? If you see given, RCT confirm there's a credible efficacy safety signal versus appropriate comparison. If it is PCT or RWE, it verifies effectiveness, subgroup performance, adherence, and real-world safety. And also, it estimates quality adjusted outcomes and utilization. Okay, what is the value test? It combined with economical modeling, right? That is the value test here. And what is the policy? If PCT shows meaningful net benefit in real settings at an acceptable cost, it proceed to coverage and like possibly conditional. If evidence is mixed, consider coverage with evidence development tied to ongoing order. If forced to pick one data set for a funding call, if I am a policymaker, I'll choose the PCT, like you all told, provided basic efficacy was already shown somewhere. So that is my idea, provided basic efficacy was already shown somewhere because it best predicts the outcomes, means PCT. It best predicts the outcomes and cost my system will actually experience. Okay, team? So what we have seen the key features, they are broader in scope, means that's PCTs, they are broader in scope, conducted in real world settings, use flexible protocols, focus on patient centered outcomes. So They don't replace art cities. Instead, they complement them, adding validity to the rigor. Okay, next slide, Richa. So now comes to comparing effective research. Okay. Now let's zoom out further. Pragmatic trials, pragmatic trials are just one piece of the puzzle. The larger framework, Richa.
Sharmila, actually, we have 30 minutes left, and Akansha
Okay.
is still to deliver, and we have to take questions as well. So
Okay.
just keeping a check on the time. Okay.
Okay.
Okay, and
Okay,
I
Richa.
see some lot of questions from people. Right. Okay.
Okay, no problem, Richa.
I'll just
Can
share
you
my screen.
please share the screen? Yeah, thank you.
I was with sharing, I was not able to unmute myself. So
Yeah, no
Yeah.
problem, Richa. Yeah. So, okay, guys, I thought I want to explain the activity, but I'll give the activity for you people. Like Richa, go to slide 21. So 20 means next slide, Richa. So this is the activity. I think it is shared for you. So see, I have done this activity for type 2 diabetes. So in the same way, you people do for hypertension. Okay. Like I can tell hypertension in elderly patients. So it is disease is type 2 diabetes. You choose hypertension in elderly patients. Do this activity for the next session. Richa, you can just go to. So that's wrap up all the observational. Yeah, you will
we can
give
give this as an assessment,
as an
assignment.
assignment, right? No
Yeah.
problem. Yeah. This wrap up observational designs and pragmatic trials since here. I'm now handing over to Dr. Akanksha. You will lead decision analytical modeling basics. Thank you. Thank you, Richa.
Thank you, Sharmila. Thank you. Hello, everyone.
Sorry.
Very good evening.
Sorry, Akanksha, I have taken so
No,
much
no,
of time.
please. No. It's okay. Thank you for having me. Okay, so after understanding about different types of trials, different types of studies, let's deep dive into the
Akansha, voice is breaking. Can't hear.
economic part of it. Earlier in the previous voice, let me just.
Breaking. I cannot hear.
Is it better now? Is it better now?
Yes, definitely.
Okay. So right.
I'm not able to present the screen. Can you see my screen?
I can't see. The screen is not shared.
No,
Can you
Richa.
No.
No.
Okay, just 1 second. I don't have the rights now. Can you please give me the rights, Climate team?
Okay, till the time
Akansha, I hope you're not sharing, and
no,
Sharmila,
Richa,
you're
no.
also
No,
not sharing.
Richa.
I
I'm not
have
sharing.
limited access to internet, so I'll be just speaking.
Okay.
Meanwhile, they are fixing the internet.
I've just given you the right now. Sorry.
Okay.
Okay, let's just quickly recap through what we learned about economic evaluations last time. So last time we understood about what HEOR is and how economic evaluations, take a part in it, and what is it? Why is it important to know? and we discussed about different types of economic evaluations. Okay, just to brief you about it, you have the recordings also, but just to brief you about it. So there are four basic economic evaluations. The first one being cost minimization, then cost effectiveness, cost utility, and cost benefit analysis. Okay, now in all of these you have the cost word in the beginning, and then you have different types of effectiveness measures which are measured in different types of economic evaluations. In the first one, the cost minimization, there is no the efficacy has to be same for both drugs, both the comparator drugs or interventions. The efficacy has to be same, and then you are just comparing the cost of the interventions of the two, three, four, how many interventions you are actually comparing. Okay, that is cost minimization. The one with minimum cost is considered better. Okay, no comparison in terms of effectiveness. Then comes the cost effectiveness and cost utility analysis, where you are actually comparing the cost of your product or intervention, and also you're comparing the effectiveness measure of your product, how much quality it is adding to your life, how many life it is increasing, how survival of your life, how the patient is surviving more if or less with your intervention or with other competitors which are available. So this is how you actually compare the effectiveness of the drug. Okay, and the last one is cost benefit, where the benefits are sometimes how much revenue the intervention has saved, revenue generated, or maybe how much cost savings, how much hospitalization was reduced. So the benefit is not exactly in terms of uh, monetary values, but you actually convert them into monetary value, the benefits in cost benefit analysis, and then you compare it with your other comparator interventions, which comparator drugs or any programs, whatever is available, whatever is your core which you are actually comparing. So okay, this is the broad basic types of economic evaluations which you do when you are actually doing economic evaluations. Now, why I recap that quickly is because these economic evaluations are backed by certain types of decision models. Like, uh, how do you calculate the total cost? How do you calculate the total effectiveness over a period of 10 years, 15 years, 20 years, 30 years? The economic evaluations are done for long durations, okay, not just for 1 to 3 years. In that case, you would try to actually simulate a real world scenario from a mathematical modeling. Okay, and for to do that, you need certain types of decision models in place. So these are the decision models which actually back at the which are playing at the back to actually generate those cost and effectiveness measures which you are actually comparing in your different types of economic evaluations. Okay, right? Okay,
Ansha, you there?
go into now what are use when we are doing different economics. Next slide, please, Rita.
Yeah.
I can see the slide moving.
Can you see now?
Hope I'm audible now.
Now you're audible,
Yes, yes,
Akansha.
yes.
In
I can
between,
see.
there was a break, but now you're audible. Yeah. So
Okay, okay.
decision tree models. Can you see the slide?
Yes, yes, Rita,
Okay.
definitely.
Okay. Go ahead.
Okay. So when we talk about decision tree models, these are structured approach used in making decisions that help in evaluating different options and their possible outcomes. Okay. Very commonly used in healthcare, business and finance also, and research, where you want to assess the risk, benefits, and cost associated with different options or different choices. Right? So how do you do that? It's just like a tree like structure which you can see on the right side of your screen on the slide. it's a tree like diagram with different branches where you try to actually capture different possible decisions or choices which are there, and the ultimate outcomes from those choices. Okay. And then what you do is you assign probabilities, like how, what is the possibility of having a choice A, B, or C, of like considering choice A, B, or C. You assign probabilities to those branches. Okay. And after doing that, you also assign the cost associated with selecting that particular option. Okay. So the probabilities and cost and the quality, the effectiveness measure which comes uh, along with that choice is also assigned. And then you do the calculations for the cost and effectiveness measures, and then the analysis. This is the way you actually do a decision tree analysis. Ultimate objective is to get the total cost from each option which is available, total effectiveness measure with each option, and then compare it. So decision tree do that for you. Okay. Now, when should we use a decision tree? This should come to your mind, and why and when should I opt for a decision tree to do my cost effectiveness analysis or my costing analysis? It's best when your decisions are short term decisions, like should I go with the okay, you have a certain budget with you. Now it's not associated, okay, the example is not associated with healthcare, but then let's have a healthcare example. You are a hospital and you are setting up your radiology department, and you have a certain budget. Okay. And now you want to allocate that budget in your radiology department for different options, different kinds of imaging devices maybe. Okay. Now it's up to you, which would you prefer. It's a short term decision, which one would you like to have. Okay. And each one has its own pros and cons. Okay. So like for short term decisions it's best. Other situation is short term health conditions, where you have very well defined directional pathways, like disease conditions where you don't have reoccurrences of disease. You don't have like coming uh, patient do not go back from advanced state of disease to like patient, for example, a patient diabetic patient.
Hello, Akansha. We are not. I mean, are you guys able to hear her?
No, ma'am.
No, ma'am.
Okay.
Diabetic
Okay.
patient can go back to the
Akansha.
diabetics. Okay.
Akansha.
So this these stages are
Hello.
go from one health state to another.
Akansha, we were not
Hello.
able to hear you for few seconds. Can you repeat the last few sentences?
Okay. Okay. I think there is network issue here. Okay. So it is best for short-term decisions, the decision model. The other situation, short-term health conditions. For example, you have acute migraine attack. So either the migraine will get cured or
I,
not get cured. Okay. Simple
your voice is breaking.
problems with limited time horizon. Reconnect. Okay. Give me a moment. I'll leave the call and I'll reconnect. Is it better now?
Please proceed. Let's see.
Okay, okay. So the limitation of this type of analysis, decision, this type of modeling is that it cannot handle the reoccurring events, as I mentioned, like the disease conditions where you have health states, which where patient can move back from advanced state to, the basic ones. So these type of modeling is not for those conditions, not suitable for chronic conditions, not suitable for chronic diseases. Next slide, please. So see, this is a basic structure how a decision tree looks like. Okay, you have a disease A. It's an example. Disease A. The first, the node here, the node is the square, which is the decision point between different treatment options. So either the patient for disease A will take the drug A or B. Let's say here you have only two options. You can have more than two also, as many options you want to compare. Then from this square node, you will go to the different possible events which can happen after taking that drug. So patient can survive or die. Just a vague example. Either the patient survive or die after taking the drug A. Now, the ones who survive, either they have a severe disease or moderate disease or mild disease. So mild, moderate or severe disease, they still have. Okay, they are not completely cured. So this is the way how you actually try to uh, put out all the possible outcomes which are happening in your disease or in your intervention. Okay, and the triangle at the end denotes the terminal node. It means where you want to stop your analysis. Okay, at this point you will from this point on you will not apply options any further options, and you will start actually now putting up all the transition probabilities, and the effect measures and the cost which I mentioned about earlier. Next slide, please, Richa. Here, see one example. A pharmaceutical company wants to introduce a medicine for a rare disease which was earlier only treated by surgical process. Okay, let's. This is an example. Now you have your square node, which is your uh, choice nodes. Here you will start putting out all the choices which you have for your intervention, for your drug, for your disease. You have earlier you just had surgical intervention as the title mentioned. Now you also have a medical treatment. Okay, now I have put the cost for each here already. Okay, so 500 rupees and 300 rupees for each one of the option. Now with both the options, what is the possibility? Either the intervention, surgical intervention, or the medical treatment gives you good results, intermediate results, or bad results. Either the surgery is successful or partially success, not 100%ly, not 100% patient is cured, or the surgery wasn't successful. Okay, similarly with the medical treatment, either the patient completely, so like 100% cure happened, or 50-50%, or medical treatment didn't work with the patient. Okay, so these are different possibilities. Now with each possibility you will assign the probability. What percent of patients out of, like, let's say total patients, 100 patients started at the square, and 50 took surgical interventions, 50 took medical intervention. Now out of that 50, how what percent of patients will have each one of these possible outcomes? Okay, the probabilities will be assigned. Similarly for the medical treatment, and then you will actually put the the cost as related to that that option, also the effectiveness measure of that option. Okay, so I have mentioned like cost, it is 1000 If the result is good, you have the cost, overall cost was 1,000. With intermediate results, you have 1,200. Then for bad results, the cost was 1,500. Similarly, for the other arm. Now the qualies also are mentioned 20, 15, and 10. So the for bad results, the quali gain is 10. For intermediate result, the quali gain is 15, and for good results, the quali gain is 20. Uh, any thoughts on what is quali? I'll take a pause and I would like to know. Uh, can you, anybody would like to volunteer and tell me what do you mean by a quali?
Quality adjusted life years.
Yes. And what does it mean? How, what, what is its formula? How do you do calculate it?
It is the multiplication of life years gained and the quality of life.
Exactly. So basically, guys, those who don't know, it is a measure where you actually, it is a way of measuring the value and benefit of your health outcome, and it is made by two components: length of life and the quality of life. So if you multiply the quality of your life for particular number of years, like I am, uh, okay, let's say I am 50 years old, okay, and for 30 initial 40 years I did not have any illness, so my quality of life was 1. So the quality of life is measured in terms of utility. Utility is a measure to calculate quality of life, right? And it usually lies between 0 to 1. 0 being the state of death, like the person is no more, and 1 being the perfect state of health. All right. So I said my quality of life up to 40 years of age was, I was in a perfect state of health, means the utility value would be 1 up to 40 years. Okay, so 40 multiplied by 1 gives you 40 qualies. That is the quali up to 40 years of age. But once I crossed 40, I was diagnosed with a chronic disease and my quality of life was no more 1, perfect score of 1. Okay, it went down to zero point 0.5. Let's say it's just an example. Okay, now from 50, 40 to 50 years of age, for, for those 10 years, my quality of life was zero point 0.5. Okay, if you multiply that zero point 0.5 with 10 years, what would be the value? 5. Now you add up 40 plus 5. 45 is a total quali associated with my life. Okay, up to 50 years of total lifespan. Got it? Clear? This is how you calculate qualis. And so quali was a measure used in this example to quantify your effectiveness of that particular intervention. Okay, so you have the total cost for each option, you have total qualis for each option, and then you do the calculation of total expected cost of your surgery versus total expected cost of your medical treatment. So look here on the right, the blue square, you will see what I did was 500 plus 0.35, which is the probability of having good results, multiplied by the cost, plus zero point 0.4 is the probability of having in intermediate results, multiplied by the cost of that option. Then you add bad results probability, then you add up the uh, cost due to bad results by multiplying the probability of that option with the cost of that option. Okay, so this is the way you have a total expected cost of your surgery. In the similar manner, you will do the calculation of qualities of total qualities which you gain from that, from surgery. So this is how you calculate qualities. got it? And you
Akansha,
add up all
again,
of them to
the
finally.
voice was breaking. Last sentence again, please.
Okay, so similarly, one, the way you do the total cost of surgery, in a very similar way you do the quality of the you calculate the total quality of your surgery. So for each option, good result, intermediate, or bad result, you have the probabilities. You multiply the probabilities with the quality of that option, like 0.35 multiply by 20, 0.4 multiply by 15, 0.25 multiply by 10, and you add up all of them. That would constitute your total qualities of your surgical intervention, right? In a very similar lines, you will do the same exercise for the other option. If you have had more than two options like surgical intervention, medical intervention, chemotherapy, anything else, you can have all the possible outcomes, and you can have all the like you can create similar type of choice or options for each one of them, and then you can do the same exercise for all of them. Okay, so this is the way how you do a decision tree analysis. Now, at the end, in the yellow, you can see incremental. We have calculated the incremental cost per poly gain. So, what do we do? Like I told you earlier, you have the total cost of your intervention and the total cost of your comparator, and you do the subtraction of both. So you have to calculate the incremental ICER values, which is reported in a cost effectiveness or cost utility analysis. You do a a ratio of difference in cost divided by difference in the effectiveness measure. So here different in cost, you have the intervention cost of intervention minus cost of your comparator divided by the cost of your divided by the effectiveness, the qualities of your intervention minus qualities of your comparator, and this is the way here it is done. So 1660 is the cost of your medical treatment minus 1705 is your cost of surgery, which was your comparator, which was available earlier, medicine, your new, the qualities of your new intervention minus the qualities of your surgery, which gives you 15. Like with every quality gain, you have to pay additional 15 rupees. Okay, this is how you interpret it. The so this actually means that with surgical intervention you will have to pay extra. How much extra? For every poly gain you will have to pay 15 rupees extra. Now you might argue that should we really be having an option which where you are paying more? So with medical treatment, you will have to pay 15 rupees extra, which means that surgical intervention was was better. Does it mean that? Yes. Like not really. Now here you need to know that this, even after paying 15 rupees extra for your new intervention, uh, do we really want to consider it, include it, consider it, even consider it? So the answer is you will have to compare this value, the ICER, this value, with your willingness to pay threshold. Okay, how much the patient is willing to pay to get additional quality of life. You can actually read about more about willingness to pay. Okay, so this is the concept which comes into picture when a new intervention is actually costing more. How much it is costing more? If it's only costing 15 rupees and the patient can actually afford to pay 15 rupees extra for a better quality of life, right? Why wouldn't he pay or she pay? They would pay, right? So this is the reason why
Hello, Akansha.
so to hello
There
hello.
was, yeah, few seconds. There was a lag. If you can repeat. Yeah.
So I was saying that the concept of willingness to pay comes when your new intervention is actually costing you more. If your intervention is costing you lesser than your previous intervention, obviously it's a win-win situation. You will definitely say that your new intervention is dominant. But when you have to pay out of your pocket extra, then you actually need to compare that cost, that ISO value, with your willingness to pay threshold. Okay, if it's below that, then you should say that the new intervention is actually cost effective. It is even uh, okay. So there is a question how to determine willingness to pay threshold. So there are studies. So there has to be actually proper studies conducted to actually know willingness to pay threshold for a particular country. Like for US, there are US, UK. For many countries, for developed countries, they have a determined willingness to pay threshold after conducting a lot of studies. Okay, population studies. But in other settings, in other geographies where the threshold is not determined, they consider the gross domestic gross domestic product, GDP, as a benchmark. Okay, so if the GDP of a country is like for India, uh, uh, okay, question, anybody, what is the GDP of India? GDP per capita, Indian GDP per capita. Okay, you can Google it. We can You can tell me that in the next session. So GDP per capita would be considered as the willingness to pay threshold. Now GDP per capita is not all. It can the willingness to pay threshold can vary from one time of GDP per capita to three times. So for developed countries, usually one time is considered. For developing countries, for developing countries or mid to low income countries, up to three times of GDP is also considered. Okay, so in Indian settings, I would say 2 to 3 times of GDP per capita can be considered as a willingness to pay threshold. You need to go back to actually check the publications what have been used previously, which has been accepted. You can refer that. Okay, next slide, please, Richa. Next is Markov model. You understood decision tree analysis. Now let's. This is another type of mathematical modeling which is to uh, uh, used to actually do the cost effectiveness or cost utility analysis. Next is Markov model, which is a mathematical model when you simulate. Actually, you try to simulate the progression of disease over time in a natural way. Okay, you in this you actually understand the disease, how in a natural way disease progresses. So you determine different health states. Now patient from non-diabetic would be pre-diabetic, from pre-diabetic would be diabetic, and diabetes, within diabetes also they will have low, medium, high levels of, like, the based on their HbA1c. I'm just giving an example. Based on their HbA1c, we can say this is severely diabetic, moderately diabetic, or mild diabetes he has. Okay, so this way you need to actually first know the disease, and then you actually try to using the mathematical model, you try to simulate the progression of disease over time. It is especially useful for chronic conditions where patients move between different health states repeatedly. Okay, so it is useful for health conditions where patient move between different health states repeatedly. Like if the patient is healthy, he goes to sick, or he might get back healthy over a series of period of time, right on the right side, you can see an example of a HIV patient. Okay, so this is a Markov model. This was a Markov model for HIV disease, and these were the different health states they determined to actually simulate the model. So based on the CD4 is a type of a cell. Based on their levels, they actually made different states. State A, B, C. C was the state where it was diagnosed at AIDS. Before that, those were like precursor to diabetes. Okay, so state A, where the CD4 cell was 200 to 500, then less than 200, and at stage C, it was diagnosed as like confirmed as AIDS. Okay, and the other state, the end state was disease, death. If the patient is dead, they would for that patient the cycle will end for the cost and for the qualities. Now we actually, by doing this, we are actually we actually try to simulate a population in a real world scenario. Like there would be a population. Think think rationally that okay, you have a country. In that country you have certain population. Not everybody would be having a disease, right? There would be a proportion of patients who will have disease, and not everybody will be in the same state of health. They will be at state A, B, C, D. Okay, and they all will progress differently. So to simulate that, we actually do Markov model. Okay, some will go back to healthy state, some might progress, some might remain in the same health state. So this way you actually try to simulate. And in this diagram, if you see the arrows, direction of arrows is actually showing the possibilities how the patient will move in that disease through in the journey in the series of time periods. So the patient in state A may remain in his own health state. He may move to state B, he may move to state C, or he may die at state A also. Okay, and at state B, what can happen? The patient of state B will not cannot go back to state A, but he can to progress to state C, or he may die, or he may remain in his own health state B. Okay, now state C again cannot go back to state B, but the patient with AIDS may remain in AIDS, will remain in that particular AIDS state, or he may progress to death. So this is the way how you actually try to simulate the progression of disease also. There might be other conditions where patient can move from higher health state to lower health state, like patient from state B might go back to state A. That depends on disease. So I began the this slide saying that you need to first understand the progression of natural progression of disease over time. Now the structure, what is the structure? Individuals move between different health states in cycles. Okay, so you will determine a cycle, like after which the transition of patients will happen. This is an assumption that all patients will move at that particular in after that particular cycle. Okay, the cycle can be for a week, for month, for year, 6 months. Anything could be a cycle based on your disease. Okay, or based on the data you have for that particular disease. There might be clinical studies where you have for the same disease you have transition probabilities, or your uh, transition probabilities for monthly maybe, or for 6 monthly maybe. Then it's your call to see which one should I adopt. Excuse me. Okay. Now, when should we choose Markov model? For chronic diseases which progresses over time, or conditions which involve repeated events or long-term risk. So these are the conditions where you should go for Markov model. Now, in the for the same diagram I showed, this is the transition matrix, like the patient from state A. What is the proportion of patients who remain in state A who goes to state B, C, and D? Now the sum of all these should be one. Like the patients at every level, at state A level, B level, C, and D, the sum should be 1 at the end. Like you should be able to trace all the patients at the end. If the patient, if even if the drop, if the even if you are considering dropout of the patient, like not in this condition, but in other diseases where a patient, uh, are no more a part of your Marco, no more a part of the treatment, then you need to consider that also as a health state, okay, or a subset. Next slide, please, Richa. This is an example of how a Marco trace is developed. So you on the left you have cycles, number of cycles which goes into the model. Okay, it can be the cycle can be yearly, monthly, weekly, daily, based on your the type of evaluation you are doing. Then you have different health states mentioned on the on each column, and you start with a certain number of population in cycle 0, like at beginning of your model, and then based on the transition probabilities you actually try to put put in like which patient out of state A. Like we are assuming here that all the patients were in state A at the beginning of the model, and then they are digressing and moving to other states. Now at each health state you need to now after year one, you have you have patients, different number of patients in different health state. Now these will all move from one health state to another based on the transition probabilities which were provided in the previous slide, which was shown in the previous slide. Okay, so you can go back to, actually you can go back to that slide and see how these calculations were done from the recordings. Okay, so the results of the Markov trace for monotherapy group in HIV. This is an example. The trace assumed that starting cohort of 1,000 patients were beginning in state A with time horizon of 20 years. This is an assumption, but you may have like different patients at different health states based on how you want to, model. You want to showcase your model. Okay, next slide, please, Richa. Next type of analysis is discrete event simulation analysis modeling. It is an approach that actually simulates individual events occurring at irregular time for individual patients. No, it is capable of simulating the real life. It is more closer to reality where individual events, it actually tried to simulate the events which are happening at irregular time intervals. Okay, in Markov model, what was happening? The transition of patients from one health state to another was happening in fixed time cycles. But here, DES actually helps you simulate like when the next event will happen. Okay, so DES move forwards in time only when something is happening, like for example a hospitalization or surgery or death. These are basically very data intensive, so you have a lot of patient data. Based on that, DES is basically feeding into the data and understanding the data and saying, oh, this type of patient, this is a demography of the patient. Okay, he might have a event now, or after 5 years, or after 6 months, or after 10 days. Okay, based on the history of the patient, based on the basically the information about the patient. So example, let's say we imagine a patient, imagine modeling a hospital emergency department. We are trying to model a hospital emergency department using the discrete event simulation. Patients will arrive at different times. Okay, they will wait in queues, undergo tests, and receive treatment. So DES is actually able to simulate this patient flow, you including the waiting time, the resource use in details. So it's basically more simulation intensive, more programming intensive. It is not done in Excel files usually. Okay, it uses specialized softwares to it requires basically specialized softwares. Okay, and it's complicated to build very intensive, data intensive. Advantages क्या हैं? What are the advantages? Models real world complexities, handles resource constraints and timings. It actually simulates the individual variability, so it capture real world complexities, and there is no fixed cycle. So you don't have to assume, okay, this has to be so there is no assumption. Actually, it is more close to reality. Okay, next slide please. Next is microsimulation models. Microsimulation models is basically simulate individual patients moving through sets of predefined health states. Very similar to Markov model. You have predefined health states, and the individual patient will be moving through a set of predefined health states over time, just like Markov. Time again is cycle based. Like in Markov model, the transition probabilities were applied in cycles. Here also, transition probabilities are applied cycle based. The difference here between the Markov and microsimulation is within Markov model you are simulating population, so it is based on the population level data. ठीक है. Data which goes into Markov, simulating the Markov is all the transition probabilities and everything is based on the population level data, data from clinical trials which is coming. But here in my Markov model, it is individuals who are being simulated. It is not group of people or number of patients. It's one patient who is simulated, and the data, this disease, the simulation is happening disease and treatment one patient at a time, not many patients like in Marco. Okay, and it actually traces the histories of individual patient history and the differences in their the how different the patient, each patient would be, and based on that his difference, how the treatment should be done. So more or like the oncology treatment, it is more individualized, right? Not every patient in cancer get the same kind of treatment, so it's more individual based treatment based on the individual history, his heterogeneity. That is included, that is considered in Markov model. And to understand the heterogeneity and individual history, it is again data intensive. Okay, so you need a lot of data to feed into the model to actually understand the individual heterogeneity and the individual variability, and uh, it is best when you have patient level data. It is best when you want to do the individual. You want to actually see individual variability, like in diseases where you have individualized treatments. This is best. Okay. Advantages: it is more realistic. Again, it handle multiple risk factors, and it is history dependent transition. So it feeds on the history of the patient. Okay, so these are broadly the four type of modeling techniques. Modeling which goes at the back end to provide you the cost and effectiveness measures. Next slide, please, Richa. Quick summary: four types of decision analysis, four types of decision trees. Decision analysis: first is decision tree, Markov model, discrete event simulation, and micro simulation. General description: decision tree is the basic of all, represent different choices and their possible outcomes in a very structured format. Markov model models the chronic conditions where you have reoccurring health events, where patient transition between different health states over time, and probabilities are assigned to each transition. Okay, and the time is fixed over fixed time. The transition probabilities are applied. Discrete event simulation: it simulates the progression of individual patients over time, which where it is able to capture the variability in disease progression and time responses when another event happens. Yeah.
Hello,
Micro
Akansha.
simulation with interventions over time. When condition, yes, Richard. Just I'm wrapping up quickly. Last
No,
slide.
no, no,
This
no.
is the last. Uh, yes,
Last few seconds were breaking, so. That's
Okay,
fine.
okay,
Go ahead.
okay.
Go ahead.
Okay, okay.
Mm.
So, micro simulation, was it clear up to discrete event simulation?
Yes.
Okay. So, micro simulation again, it simulates individual patient characters and their interaction with the interventions over time. So, individualized the patient who have individualized type of treatment, the micro simulation is the best. Best when which one should be used when decision tree when the condition is short term and with well defined unidirectional pathway. Markov when the disease is chronic. Discrete event simulation when you have complex healthcare system and individual patient pathways are different, individual patient reaction differs. Micro simulation where you have more you have personalized treatment strategies and heterogeneous population is there. You want to cater heterogeneity also, and you want to have personalized treatment. Micro simulation is the one to go. Example for it, decision tree के लिए you choose between two treatment options for acute infection based on their cure rates or and their cost. Like one example we gave for surgery versus medical intervention. Markov, if you want to evaluate a long-term cost effectiveness of cancer treatment over multiple years. Okay. Discrete event simulation when you are actually evaluating the impact of personalized medication in oncology. You can use DES also in that case, because in that case you will be actually simulating when will there be any reoccurrence, will there be any metastasis. So DES can be used if you want to. And my example for micro simulation is if you want to see the impact of like a smoking cessation program in different demographic groups, like in in the patient people with different demographics, what would be the impact of smoking cessation. So DES and micro simulations are more individual based. Micro simulation has fixed cycles, fixed cycles, and also the health states. But DES doesn't have any fixed health states, and it just try to simulate the progression by uh, estimating the event time of next event. Okay, next I think this was it. This was the last slide. Open to questions.
Yes, so we have little time left, and quickly, we received a lot of queries regarding last week's assignment. So I'll quickly just paste a few more examples. What we wanted in that. So we wanted you to search in different HTA bodies. Is there any decision they approved for reimbursement, or it can be a decision that they upheld for reimbursement? Okay, so I'll just paste one example. I'll paste a few. Okay. So then, and you can copy paste it if you want in your thing from the chat. I don't know if it is possible. I'm just skipping all the questions. Right. So, yeah. So just one last question I saw before pasting: on which software these models are performed. Can be Excel, can be R Shiny, okay, can be Python.
So DES and micro simulations are usually based on like Python and uh, language models. Okay, those are more complex ones and can't be done on Excel, basic Excel.
Uh,
Too heavy
I,
for
yeah.
others can be done on Excel, Triage, R Shiny, and on any other software. Okay.
Yeah, I the examples that I'm trying to paste here are pretty long for the chat session. Climate team, can I send you the examples? Maybe you can share with the students. A couple of examples I'll share. Okay. Yeah. Okay. So quickly, Akansha, would you like to take some questions if you see anything?
Yeah, this one is interesting.
Hmm.
Tushar asked, ma'am, but GDP would not factor in the gaps in the income. The difference in level of income is high in people. So GDP, I have answered you also. So GDP based willingness to pay thresholds suggests that 1 to 3 times of GDP per capita. Okay, and those are national average national measures. So they do not come from a particular class of people. So it's average based on the national income. Definitely, they don't account for income inequity, but yes, nowadays we are more coming up with types of analysis where we are brainstorming with, having inequality also in our mind. So maybe next few years, more equity based willingness to pay would be seen in countries where there is a lot of inequity. You never know, but at the moment average national income is like used 1 to 3 times. Okay. Next question: are the probabilities in decisions simply taken from prior studies, or are they calculated from data sources? Sometimes they are available from the prior studies or clinical researches. Sometimes they are calculated. Okay. Any other question? How to determine willingness to pay threshold? I think I've answered this. Willingness to pay threshold is 1 to 3 times of the GDP as recommended by WHO. Um, these were the questions. Okay, I think I've covered the questions.
Ma'am, just one question.
Yes.
It is with respect to the example you had given regarding 50 years and 40 years. So you mentioned that if we calculate, assuming that from 40 years of age you have a chronic disease, then your calculation comes out to be somewhere around 45 years, right? As per your example.
Hmm. Yes.
So then are we saying that at 50 years, so like I'm just confused that you are still 50 years of age, but you are saying that the value is 45. So if you could elaborate on.
Yeah. That's the crux of it. Quality of life, quality adjusted life years. Because I'm not living with 100% of perfect, like the full perfect health up to 50 years. The my health deteriorated when the quality of my health deteriorated when I had a chronic disease. Okay, and that has been incorporated. So therefore, that I wanted to explain the quality adjusted life years, what exactly it means. I am by age 50 years of age, but my quality is 45 years because I'm not in a perfect health state of health. Okay, getting my point.
Yeah, yeah. So
So
it's
it's
just
not
to indicate that you are not living your health, like, optimal health.
exactly.
Okay,
So this
understood.
is the concept of quality adjusted life years. Okay, you will
Yes,
very
ma'am.
frequently find it in the economic evaluation papers. This was just one example I gave you, but there are studies where you actually calculate qualities of different qualities of patients in different health states. So I just wanted to give you example of how it actually is calculated, right?
Yes, ma'am. Understood.
uh, I think, Richa, we are good. I think I don't find any other questions. We can close the
Sure.
call.
So I'll just share the examples of week one assignment. I'm almost done with that. And week two assignment I've already shared. You will get that. Okay. So see you soon, everyone, next week. Please complete the assignments and quiz. Okay. Bye bye. Have a good evening. Thank you,
Bye bye.
everyone. Bye
Thank you,
bye. Bye
everyone.
bye. Bye bye.
Thank you, ma'am.